Thank you all for coming. If you were here at last month's talk, I was complaining about the snow that was out there. So this time, instead of snow, we have cold weather and wind. For the May lectures, we're going to have fields of locusts come in. So we're trying our best here. At least this time, the cherries are blooming. In any case, this is the second of our 2018 neighborhood lectures. We've been very pleased to see your attendance, and we hope you're enjoying these. And I have a particular pleasure today in this one to be able to introduce Dr. John Mulchaey. John is the director of the Observatories of the Carnegie Institution. I've mentioned to you, for those of you who've come to our lectures before, on this campus there are 2 out of 6 of the departments of the Carnegie Institution. There are 3 on the West Coast, and there's 1 up at the Johns Hopkins campus. We have the director of the Johns Hopkins Embryology Department here, not the Carnegie Embryology Department on the Johns Hopkins campus is here. But John Mulchaey will be speaking today. He's both the director of the observatories, and both he and Yashen Zhang have been the interim presidents while we're looking for a new president that we hope to have on board very soon for the institution. John got his bachelor's degree at the University of California, Berkeley, and then as a sort of a local boy coming out to the University of Maryland to get a PhD in astronomy, and then went over to the Space Telescope Institute. One of the many things that he's done in astronomy is he discovered a galaxy that has a large contingent of hot gas in it, which may sound like a rude thing to you, but the important observation of this is that for gas to be hot but still be around in a galaxy means that something is holding it there, some gravitational force. So this was another bit of evidence for the existence of dark matter that has a gravitational attraction but does not emit light, and hence basically holds the universe together, if you will. So John, as I mentioned, runs the observatories out in Pasadena, but the main role out there is actually to maintain and operate the observatories of the Carnegie Institution that have a large number of telescopes that are down in Chile, Las Campanas, Chile. John will tell us a lot about that operation, I think, tonight. So John, without any more, I'll pass it on to you. Eyes on the Universe, Carnegie's Leadership in Astronomy Today.
All righty. Is this loud enough? Everybody's okay? Good. Excellent. Thank you so much. It's so great to see so many people come to our talks. This is just, it's really wonderful to see interest in science. Today I am going to, as Rick said, I'm going to really talk about the astronomy portion at Carnegie. I will say off from the start, because we are on this campus where there are astronomers that you probably have heard from before, I'm going to say very little about the astronomy that actually happens here, because I'm assuming you hear from those individuals. So I'll say a little bit, but I'm really more going to talk about a lot of the astronomy that we're doing in Pasadena, simply because that's something you don't hear too much about. Astronomy at Carnegie goes way back to the very, very beginning of the Carnegie Institution for Science, and is really due to these 2 gentlemen here. Right there on the left you see is Andrew Carnegie, of course, who at the turn of the last century was one of the wealthiest men in the world. And Andrew Carnegie, as you know, gave away much of his fortune to do lots of great things, set up many institutes, set up many libraries. The man to the right of him is George Ellery Hale, who at the time was a solar astronomer working at the University of Chicago. Hale had at that point built the world's biggest telescope outside of Chicago in Wisconsin. And Hale quickly realized that Wisconsin's a terrible place to do astronomy for the very obvious reason. So it seemed like Washington would be a terrible place to do astronomy too. The weather. You really need to be in a clear location to do astronomy. And so Hale was convinced that Southern California was in fact the place to do astronomy because of the climate we have where it's clear most of the time. Hale read in the newspaper that Andrew Carnegie was giving away his fortune, and he arranged to meet with Carnegie and convinced Carnegie to build an observatory in Southern California. And that is how my department, the observatories, got founded. And that's why we're in Pasadena. But Hale didn't start with just building one observatory. He really, in the end, built the world's best series of telescopes. In fact, he built the 3 biggest telescopes in a row in the world. And it's these telescopes that really defined all of modern astronomy. Those of you who know Los Angeles, Mount Wilson is where these telescopes started. This Mount Wilson is located above Los Angeles. I'll show you some pictures in a little bit. And these telescopes, the Mount Wilson 60-inch had first light. The first time we used it was 1908. The Mount Wilson 100-inch had first light in 1917, which in fact this telescope, I argue, is the most important telescope ever built, which I'll explain why in a minute. And then for those of you who know Southern California, Palomar is down near Temecula, which is near kind of between LA and San Diego. Anyhow, Hale, using funds from Carnegie and others, really established all of modern astronomy because of these telescopes. So why do I say that one telescope, the Mount Wilson 100 inch, is the most important telescope ever built? The reason has to do with this gentleman here, who is a Carnegie astronomer and one of our more famous Carnegie scientists, Edwin Hubble. So you all know the Hubble name. You know the Hubble name because of the Hubble Space Telescope. The telescope is named after Edwin Hubble because of the two remarkable discoveries he made in the 20s. And I argue these two discoveries are the most important discoveries in astronomy in the last 400 years. So let me tell you a little bit about what they are. The first is, in Edwin Hubble's time, there was a real debate about the size and scale of the universe. And in fact, most folks thought the universe was a single collection of stars, we call the Milky Way galaxy now, and was relatively small. What Edwin Hubble did was he used a technique. He found a very special type of star that we call a Cepheid variable in the nearby Andromeda galaxy. And with this star, this type of star allows you to measure the distance to it in a very clear way. And when he did this, you'll see October 1923, based on that one star, he was able to measure the distance to this fuzzy, what was called a nebula, and realize, in fact, it was a system much, much further away than anybody realized. It's a couple million light years away, which is pretty big. And so instantly, Hubble took the universe from being this small collection of stars to being an immense system, filled with other systems like the Milky Way that we now call galaxies. I'm going to talk a lot about galaxies. So I consider this the most important result in 400 years in astronomy. To remind you what happened 400 years earlier was the work of Galileo and Copernicus. So you'll remember that for a long time, humans thought we were the center of the solar system and the center of the universe. It was the theory of Copernicus and the observations of Galileo that moved the sun to the center of the solar system. This was an earth-shattering idea, right? Similarly, I argue Hubble's result is at the same level because he once again took the universe and kind of redefined our understanding of the universe. That's a pretty remarkable discovery. So, but if it wasn't enough, about 5 years later, Edwin Hubble, using those same telescopes at Mount Wilson, went on to show that the universe is expanding. And this is an equally important result in some sense. Because if you think about something that is expanding and you trace it back in time, it means it had the beginning. And this was the first time in 1929 that people really thought of the universe having a beginning. This is, of course, the central component of the Big Bang Theory, which, not the television show, but the model, to say that now. And that was Edwin Hubble's other result. These two results really defined all of modern astronomy, and were done because of Carnegie's activities in Southern California. Now, in the 20s, Edwin Hubble was a huge celebrity in Southern California because of this work. Edwin Hubble's here, the second there on the left. This is a picture taken from our library in Pasadena. There's one individual there that you almost all certainly know. That is Albert Einstein, of course. Albert Einstein spent a lot of time at the observatories in Pasadena working with Edwin Hubble because he wanted to understand what this expanding universe in particular meant for his models of the universe. This particular picture was taken in 1931. You'll notice this is another picture taken from the same day where Einstein was giving a lecture. This is one of the two most used pictures of Einstein. If you do a search on Einstein, this one comes up, and the other one's a crazy hair picture. But this was taken in our library. So I always like to point this out to people because you see the picture, but you never actually associate it with the amazing science that got Einstein there. The equation he's talking about there, he has on the board there, is describing the size and shape of the universe. And so anyhow, the work of Edwin Hubble really was on the map in the 20s with physicists like Einstein. Now, Los Angeles has a beautiful climate. We enjoy it. I walk every morning with my dogs in shorts, even in January. The problem with Mount Wilson is it's located above a very large city. These are 3 images taken at different times from the Mount Wilson Observatory. It is really on the edge of the city. And you can see quite easily, even in 1925, there was a lot of light pollution from Los Angeles. It's really quite beautiful at night, but not if you're an astronomer. And so for those of you who live here in the city, when you go out here and you look in the sky and you maybe see 50 stars in a night here in Washington, D.C., the reason you see 50 stars instead of several thousand is because of this light. This basically background light floods out the faint stars. This same thing that allows us not to see stars in the city makes it impossible for us to do astronomy anymore from Mount Wilson. And so recognizing this, Carnegie astronomers made an effort starting in the 60s to move operations to South America, and particularly to Chile. For those of you who know Chile, we are about 500 miles north of the city of Santiago. Now, this is what Chile looks like. For those of you who've been to Southern California, we don't get a lot of rain in Southern California. We get about 15 inches of rain a year, but we still have green things. If you look at Las Campanas, you don't see a lot of green. At this site is really, we're about 300 miles south of the driest place on the planet. Here it rains less than 1 inch a year. So this makes it an amazing site for astronomy. It's clear over 90% of the time. But it really is, this is a real desert. Now, despite that, there's actually a lot of, and this is the biology portion of the talk for the biologist I was talking to earlier. This is as biology as it gets for me. One of the remarkable things is the fact, even though it rains less than 1 inch a year on this mountain, we actually have a lot of animal life. These are some pictures here. This is a guanaco. A guanaco is, or a llama is a domesticated guanaco. My favorite is the vizcacha, which is about this big. It's kind of a rabbit meets a squirrel. The astronomers are all terrified of the tarantulas, which can be rather like that big in Chile. Anyhow, I just like to point out that even in the driest places on Earth, there's actually a lot of animal life. It's quite nice. Now, Chile's great because it's clear. It's far from any cities. We're hundreds of miles from the nearest city. The problem is it is far, right? It's far. To Mount Wilson, the astronomers in Pasadena could drive up in about 45 minutes. It takes me 24 hours from the time I leave my house to get to the top of the mountain. This is an extremely remote location. And what that means is we have to have a full crew that operates the telescopes in Chile. So we have 75 employees work full-time at the observatory. So it's basically like a little town. We have cooks, we have engineers, we have paramedics, we have everything you would need if you're hundreds of miles from the nearest town, so that when the astronomers go, they're safe and we can do our work. This also means as an astronomer, what we do is we typically go to Chile, collect data for about a week at a time, and then come back to the US and then work on that data until we go back to Chile the next time a few months later. Okay, so people often ask me, well, it seems a long ways to go. Is it really worth it? And when you see the night sky in Chile, you actually know it's worth it. This is a picture of what the night sky would look like. Actually, this is not through a telescope. Your naked eye can actually see this amazing structure here. That is the Milky Way that you're seeing over 2 of our telescopes here, our Magellan Telescopes. Now, I have to point out that Chile is interesting because it's dry and clear. It's interesting because it's very dark. But it's also interesting because the southern sky is actually better than the northern sky. And the reason for that is because our Milky Way galaxy that we live in, that's what you're seeing here, the center of the Milky Way actually occurs in the southern sky. So the sky is more spectacular in the south than the north. In addition, the Milky Way has 2 spectacular companion galaxies called the Large and Small Magellan Cloud. You can see those with your naked eye. These are very interesting stellar systems for us because they have different types of stars than we see in the Milky Way. And so they end up being very interesting laboratories for astronomers. And once again, you have to kind of go to the southern hemisphere to see them. So for all these reasons, Chile really is the place to go. Just to give you an idea, a scale of kind of our modern telescopes, our Magellan telescopes have mirrors that are about 6.5 meters across. It's about 21 feet across. So you see the back of the mirror in this image here, and you can see some people standing here. These telescopes are very big. To put it in perspective, they're about 3 times the size of the big telescopes that Edwin Hubble was using back in the 20s. These are really incredible telescopes here. And most of our work these days is done with these 2 telescopes. Okay, now, I usually don't put lists up on the board, but I had to put this list up because I wanted, before I talk about kind of some of the exciting astronomy we're doing, I wanted to have a quick look back. And this is an extremely partial list of some of the major astronomy discoveries that have happened at Carnegie in the last century. First using those telescopes at Mount Wilson, then using the telescope at Mount Palomar, and then eventually the telescopes at Las Campanas. And I'll point out here that I put in orange, this is my one thing for the DTM folks, 3 DTM astronomy results that I pulled out, which I'll talk a little bit about. I'm not going to go through this in detail, except to point out some of the things. Hale himself, not only was he an amazing man building the 3 biggest telescopes in the world, he also discovered magnetic fields in the sun, which of course has very important implications for the Earth, in fact. And he did that work at Mount Wilson. I like to point out the second one there, which is Harlow Shapley, because this is an amazing thing to emphasize, I think. In 1918, I don't think we have anybody here from 1918. We might, if we do, let me know. in 1918, we still had not learned the lesson that we were not special. Because in 1918, even though we knew, this was prior to Hubble's work, even though we knew that the sun was at the center of our solar system, people still thought the center of the solar system was still the center of the universe. And in fact, the center of our Milky Way galaxy. Okay, so that changed in 1918, thanks to Harlow Shapley. What Harlow Shapley did is he, in fact, showed that in our own Milky Way galaxy, we're kind of out in the suburbs. So I think that's a remarkable, even 100 years ago. We are not the center of everything. It's always an important message to remember. I'm not going to talk about a lot of these other ones. Vera Rubin, I'm hoping many of you, had a chance to meet Vera when she was here. Of course, Vera was the first to really demonstrate that galaxies like our Milky Way are dominated by a dark component we call dark matter. We still don't fully understand it. About 90% of the stuff in a galaxy is made of this component. That work was done right here on this campus. Paul Butler, I don't think Paul is here. Didn't see him. He's hardly ever here, right? He's always observing. Paul really should get the credit for really being the first to kind of determine the technique that is used to find planets around nearby stars. And this is a huge and very exciting field, and I'm sure you've heard from him. Our previous director, Wendy Friedman, who was before me as director at the observatories, was the first to measure the precise age and size of the universe. We know the universe is 13.7 billion years old to extreme accuracy. And I think that's an amazing accomplishment that we can date the universe so clearly. That was work that Wendy did. Work by Mark Phillips showed that not only, as Hubble showed, is the universe expanding, but the universe is accelerating. This is due to a mysterious force we call dark energy. I should point out, astronomers call things dark when we have no idea what they are. And if you add up the dark matter and dark energy, it's about 96% of the mass energy in the universe. So basically, the astronomers are studying 4% of the universe and implying the other 96%. Anyhow, the universe is accelerating due to a mysterious force called dark energy, and Mark Phillips was part of that team. And Scott Shepard, I'm sure you've heard from Scott here, who, of course, has done some of the most interesting work on the outer solar system and the search, of course, for the missing planet. Okay, now for the fun stuff. So now let me say, so that was some history, but well, let me back up one more thing and say, this list of accomplishments is the most impressive list that any institution in the world can put together in terms of astronomy. I want to emphasize this. More astronomy has happened at Carnegie than anywhere else in the world. And that's something that I take a lot of pride in, and I think all of our astronomers do. So it's really worth noting that our understanding of the universe is really due to all these great telescopes that Andrew Carnegie helped fund. Anyhow, so now let's talk about some fun stuff now. So now I want to talk a little bit about some of the things we're doing now and how these are kind of interesting and relevant questions. And I'll start with this here, and this is a really general question. The question is, how did we get here? And that's a very vague question. What I mean by that is we know the universe started in a Big Bang, but when we look out at the night sky, you see beautiful galaxies like this. This is a picture of a galaxy. This is what the Milky Way would look like if you could step outside of it. So what is this picture? This is a picture of about 100 billion stars. There would be about 1 trillion planets in the system that you don't see in these images, but they're there. And as I said, Harlow Shapley was the one who moved us from the center to kind of out here in the suburbs somewhere. Anyhow, so how did the universe go from this Big Bang to producing these amazing structures that we see like this galaxy? Well, thankfully in astronomy we have a time machine, and that's because it takes time for light to reach us from distant parts of the universe. And so I'll give you an example. In the case of the sun is about 8 light minutes away. So that means if the sun went out, we wouldn't really know about it for about 8 minutes. That's the good news. 8 light minutes is pretty close. This image is from the Hubble Space Telescope. This image was taken by pointing the Hubble Space Telescope at an extremely small region on the sky for a couple weeks at a time. To give you an idea of the scale of this image, if you pinched your fingers and went up like that, that's about the size of this on the sky, just a tiny little region on the sky. This was a blank region on the sky, according to the Hubble, before we looked at with the Hubble Space Telescope. This is what a 2 or 3 week integration on that telescope reveals. What you're seeing here are very distant galaxies in the universe. Each speck you see on this image, literally every single one, there's 3,000 in this tiny little image. Each one of these is a distant galaxy. Not unlike this in some ways. So let me remind you again. That means each one of these specks, and I mean the tiniest little specks you can barely see, are systems with about 100 billion stars and 1 trillion planets. I like to say those numbers, they're very big, but it's important to sink in. This is the portion of the talk where people say to me, you make me feel very insignificant. And you probably should, because this is 3,000 galaxies each with 100 billion stars and 1 trillion planets. The counter-argument to that is that we live on a very special planet that we, as far as we don't know of any other planets where there's people giving lectures on astronomy in the universe, right? So we are unique in some ways, probably, but there are a lot of galaxies in the universe. So why are these galaxies so small? Why don't they look like this guy? This is a very nearby galaxy. Well, that's the answer. These are very far away. This image, most of the galaxies you see are typically about 8 to 10 billion light years away. So you're seeing what the universe looked like 8 to 10 billion years ago. Let that sink in. And there's a lot of billions and trillions, I know, in astronomy, and we tend to throw them around. But this is what the universe looked like 8 to 10 billion years ago. So as an astronomer, if I want to know how did we get to these beautiful galaxies we see today, the answer is we look back in time. I can look at galaxies 8 to 10 billion years ago. I can look at galaxies that are only 4 billion years ago and 2 billion and basically today and try to study how things have changed in time. Now, this ends up being very complicated, of course, which is good for lifelong employment for us astronomers. Because, and you can probably figure it out by looking at this image, because I keep going back to this, I love these spiral galaxies. You know, this is what the Milky Way looks like. Beautiful spiral galaxy, kind of blue, white. You look on this image, there are a few galaxies that kind of look like that. There's kind of one up here, and there's maybe one there. But then there's all sorts of galaxies that look kind of, they don't have that spiral shape, and they are different colors. They're orange, and that matters because the colors are telling you different types of stars are in different galaxies. And so the reason this is interesting is blue stars don't live very long. And by not very long in astronomy, we mean millions of years. Sounds like long to humans, but millions of years. So if you see a galaxy that's blue, and there's some good examples in this image. There's a blue galaxy, for instance. There's a really blue galaxy. Those are systems that are forming stars very actively, because, at least over the last few million years. Otherwise, they wouldn't be blue. What happens when the blue stars die out? Well, they leave behind the other stars that were there, which are the red stars. So if you see a red galaxy, you're seeing an old system, a system that is no longer actively forming stars. The complications astronomers have is if you look at this image, where I'm going to say that these are all kind of around the same time in the past, they're very diverse. You see orange, you see blue, you see round, you see. The universe is very complicated. I like to describe this process like weather. It's that complicated. There's just a lot of different factors that are involved. It gets interesting because now we can trace this work even further back, and this is some more recent work by some Carnegie astronomers. This is work by Polo Infante, who works in our Chile office. A very unimpressive image. You can barely see them. But I just want to point out these galaxies are even much more distant than the one in the previous image. These galaxies he's discovered are 13 billion years away. 13 billion light years away. That means we're seeing the universe 13 billion years ago when you're studying these galaxies. The Big Bang was 13.7 billion years ago. You're seeing galaxies within the first billion years of the universe. This is very exciting. And these galaxies that he's finding here, he's finding them because they glow. It's kind of hard to see in the image here. They glow from the hydrogen gas. This gas is being lit up by those young stars. So these are galaxies that are rapidly forming stars. That's kind of what you expect in the early universe where there was a lot of gas around. Complication is another astronomer in my building, Eric Persson, was also studying the distant universe, and he found some very different kinds of galaxies that are also about 13 billion light years away. But you see his are very red. Here they are. They're very unimpressive. These are galaxies that formed right after the Big Bang, and for some reason they were almost immediately stopped forming stars. So once again, this shows you the universe is very diverse. And trying to understand why do some galaxies keep forming stars, why did some stop? It is like the weather, unfortunately. So, but the fun thing is we think that we think what happened in these cases, I like to call them prematurely old galaxies, is we think that they are probably, they may have become old because of black holes. So black holes are always fun, so I always like to talk a little bit about black holes. So what is a black hole? Well, a black hole is an object that has such strong gravity that light itself cannot escape it. It turns out that we have big black holes in some galaxies, as I'll show in a bit. This is just an artist's conception. If they're black and they don't emit light, how do we see them? Well, the answer is we see them by the material that swirls in towards the black hole, the material that feeds the black hole, because that material heats up to very high temperatures and emits light. And so what we see is we see the bright light from around the black hole. We don't see the black hole itself. And let me give you an example here. I'll show you this. In fact, I forgot I put this in here. Okay, so this is that same image I showed you before. of the galaxies. These are the distant galaxies. This is an image taken with the Hubble Space Telescope, which is a visible light or optical light telescope. You would see this with your eye if you could look through the Hubble Space Telescope. What you're seeing in a case like this in the optical light is you're seeing the stars. That's what we study with the optical telescopes. If you point an X-ray telescope at the same region of the sky, this is what you see. And what you're seeing with an X-ray telescope are black holes. This is the material swirling in towards the black hole. Because to produce X-ray emission, you need very, very high temperatures. And normal stars don't do that. So whenever you take a deep image of the sky, this is the same region in the sky. When you take a deep image and an X-ray image, you're revealing the black hole. So X-ray telescopes end up being an excellent way of seeing black holes. So let me compare those two together. Here we have, I've unfortunately reversed it. Here's the X-ray image from Chandra, and here's the optical image from Hubble. I should point out, for those of you who are less familiar, everybody knows the Hubble Space Telescope. The Chandra Space Telescope is the X-ray equivalent of the Hubble Space Telescope. And it doesn't look so exciting, maybe, the X-ray image. Each of these points here is a black hole. If you do a careful analysis, what you see is these black holes all occur in the centers of these galaxies. And so what this tells you is that even in the distant universe, all the big galaxies had big black holes at their center. And these black holes can be interesting because, let me say, how far back can you see black holes? And this is I just wanted to plug this result by Eduardo Benedos, who's one of our young postdocs. Eduardo has recently found a black hole that is one of these big black holes that is 13 billion light years away. So in other words, those very first, the most distant galaxies we see are 13 billion light years away. Even those galaxies, apparently, some of them have black holes even that far back in the past. That's really remarkable. This is just hot off the press. It's not that exciting, except this is the X-ray data for that source. This is the most distant X-ray source ever seen, so it's kind of exciting that Eduardo did. But the interesting thing about these black holes is that it appears that these black holes are there even when the early galaxies are there. So why does that matter? Well, in addition to shining this X-ray emission can also kick out all the gas out of a galaxy. And so in fact, we think that that's why the black holes kill the galaxies prematurely. Because as soon as your black hole forms, heats up to very high temperatures, it starts ejecting mass out of your galaxy, and you have no more mass to form stars. And so we think the premature galaxies, prematurely dead galaxies, could just be galaxies that had these black holes very early on. And so this is very interesting. The problem is, how do you build up a big black hole? This black hole here, you can kind of estimate its mass. It's about 1 billion times the mass of the sun. So how do you build up such a big black hole in the universe? We think you build up a big black hole by taking small black holes and combining them. The problem is, this is at 13 billion years. You don't have a lot of time. The universe started at 13.7 with the Big Bang. That's not a lot of time to build up a big black hole. So this is a huge challenge. In fact, when he found this, I'm like, this can't be true. How could you possibly have a black hole so big, so soon after the Big Bang? But the universe is telling us we do, even if we don't know how to do it. So I'll show you an example, though. This is my own work now, a little bit. This is a fun thing I did a few years ago. I was asking the question, how do you build up these big black holes? And I said, well, one way you build up a big black hole is you take two smaller ones and add them together. And so the question is, can we see that happening in the universe? And so I had a project I started, which was to look for X-ray sources right next to each other. Because as I said, if you see an X-ray source, it's likely the emission from around the black hole. So if you see two X-ray sources, that could be two black holes that are about to merge. The problem in an image like this is you don't know the distance of the black holes. One of them could be much further away, and it could be projected to be two black holes in the sky. So what I did is I saw this. When I found this one, I'm like, this looks very promising. These look very close to each other in the sky. Let me go to Chile and take an image of the stars to see what's happening in the stars. And when I did that, I got this image. And instantaneously, I knew I had something interesting. What you're seeing here now, these are where the two black holes would be, one in there and one there. These are the galaxies that the black holes are sitting in, the X-ray sources are sitting in. But the interesting thing are these things here, which we call tidal tails. These features we know from other work, in fact, by Francois Schweitzer, another Carnegie astronomer, has done a lot of work on this. When you see tidal features like this implies two objects are gravitationally interacting. So when I saw this, I instantaneously knew what we had was, in fact, two black holes that are in the process of merging. This is very exciting. This was the first time we had seen this. This is now the X-ray data on top of the optical data. So you see the tidal tails. You see the X-rays are kind of right in the galaxy. So the fun thing you can do at this point is you can go down the hall and ask your young postdocs, to do a simulation. So what I'm going to show you is a computer simulation from one of the world's experts who studies how these galaxies interact. His name is T.J. Cox, and I said, TJ, can you, sorry, let me go back. I don't want to give away that. And said, TJ, can you produce these merging black hole two galaxies? Here's a galaxy. Here comes the first galaxy, second galaxy. What you see is there a gravitational interaction. You can see how it produced these beautiful tails. These are those tidal features I was calling tidal tails. By the way, up here is time in billions of years. Unfortunately, you have to wait about 2 billion years for that second. So what has happened is the galaxy kind of went by but escaped. But gravity will always bring it back down after about 2 billion years, so we have to wait a few minutes. Thankfully, our simulation is much faster than here. So here we go. Here's the second time it comes back. This time the encounter is much closer. And you see this time the galaxies are kind of stuck. They're going to gravitationally merge. Now remember, we think we have a black hole in each case. That's my real data. This was his simulation he just pulled out. It was really quite remarkable. The fun thing is with the simulation, you can run it forward and see what happens. And what you see is that we're very close to seeing the two galaxies merging to form a single galaxy. And in the process, the two black holes at the center will form a single black hole. So this is really how we believe those black holes formed. We think it was these mergers. It's still difficult to figure out how you do it so rapidly, but this is what the universe does, and that's TJ. And so you end up with a single galaxy. Now, I know you're saying, how is this relevant to my life? It is relevant to your life, because in about 4 billion years, our own Milky Way galaxy will merge with the nearby Andromeda galaxy, the same galaxy that Edwin Hubble first measured the distance to. These galaxies are rapidly approaching each other. This is a picture, artist's conception of what the night sky from Chile will look like in about 4 billion years. And you see this, there's going to be this beautiful Andromeda galaxy coming flying towards us. So I'll remind you, what you have here is the Milky Way is a system with 100 billion stars. Andromeda is a system with 100 billion stars. So what happens when you take 100 billion stars and 100 billion stars and you bring them together? Absolutely nothing. This is the boring part of the talk. Because it turns out that space is really empty. Even though I'm saying 100 billion and 100 billion, the space between any stars is so significant that when you merge the systems together, you don't expect a single star to actually gravitationally interact in a strong way with another star. So let me put it another way. If we're here on Earth in 4 billion years, that would be pretty impressive, and the sun is still here, the sun should still be here in 4 billion years. The sun would continue to orbit the sun. You would not notice anything different, except that you would have a lot more stars in your night sky. So your future will be the merger with the Andromeda galaxy, but nothing to fear. This is a case where it's first of all far away, but time-wise, but of course, this is just an interesting thing to show you just how empty space is. I think we often don't appreciate that. Take that again, 100 billion and 100 billion, throw them together and you get nothing. Anyhow, but a lot more stars. Okay, sorry. I wanted to briefly talk about another a topic that kind of switched topics here. And this actually helps explain why the universe is so complicated in some ways, as hopefully you learned from that galaxy portion. And that is, you've often heard, what are we made of? We're made of stardust. Well, what exactly does that mean? So another major emphasis at Carnegie on the astronomy side, as well as on campus here, is trying to understand kind of the elements in the universe and where they come from. So the universe is continually recycling itself. What happens is you have stars. Oh, sorry, let me go back. I keep hitting the wrong one. You have a star here. A star is just a system, a gaseous object that has nuclear fusion at the center. So currently the sun is taking its hydrogen and fusing it to make helium. In the process, it glows. If the sun was massive enough, it's not, but if it was, eventually it would produce other elements. Eventually the helium would fuse, and you'd end up with things like carbon, nitrogen, and oxygen. But eventually those big stars end their lives, and they blow up in what we call a supernova explosion. That's the second picture here. And then this material, you have to now imagine, supernovae are going off kind of all over the place. Eventually that material will collapse back down by gravity, and another star-forming cloud will form, and new stars will form, and then you start the cycle again. So the universe is continually recycling itself. But each time it does it, it's producing more elements like carbon, nitrogen, oxygen, iron. And that's, in fact, thankfully, because otherwise we wouldn't be here, right? So this is really one of my favorite new plots I got. This is the periodic table, which you'll remember from high school, with a kind of a different labeling here. These are the elements that we know of, and it kind of tells you where the elements come from. And what's particularly nice is the human figure here. So about 73% of the human body comes from stars and massive stars that exploded. This is this fusion going on in the center, combined with the actual explosions from the supernovas. So when you say you're made of stardust, that's because about 3/4 of you, in fact, comes from these explosions. You really are pieces of star. I'll point out another interesting part. About 10% of you is mostly hydrogen. You have really no helium in you. Hydrogen is interesting because the universe stopped creating hydrogen about 13.7 billion years ago. Right after the Big Bang, all the hydrogen was created. We don't really create new hydrogen in the universe. So on those days when you're feeling old, it's because about 10% of you is 13.7 billion years old. Think about it that way. Yeah. That joke works better at 8 a.m. when you're giving a breakfast morning talk. It doesn't work so at night. You're probably feeling okay. Anyhow, but the fun thing here is to point out that really you are the product of the universe, and most of that is the product of stars. But the reason I put this up here today is to talk about some very interesting results that you've heard probably late last year, which has to do with some of the rare elements in the universe, these things that are purple. These are some of the heaviest elements in the universe, and this has been a challenge to understand where do these heavy elements come from. You're very familiar with some of them. You're familiar with platinum. You're familiar with gold. That's these guys here in this purple. And in fact, where these come from largely came from work from another Carnegie astronomer. I didn't even put this one on the list. Who first showed in 1935, made the prediction of what we call a neutron star. So that's what I'm going to talk about next. We believe these elements come from when you take one neutron star and smash it together with another neutron star, and you have a very big explosion. So what is a neutron star? I'll actually go back one here. When I talked about the stars exploding, most of the star ends up in an explosion, but it leaves behind a very, very dense core, which is the neutron star. And that dense core, to give you an idea, is typically if you took the Earth and shrunk the Earth to about 10 miles across, that would be the density of a neutron star. Let me give you another example. If you took all the humans that ever lived on Earth, that's about 10 billion, and you put us in a cubic inch, that would be the density of a neutron star. Really very, very, very dense. And this high density is needed in these explosions. When you take a high density, two high density objects, you have the right materials to produce those elements like gold and platinum. So, how does this happen? Well, the way you get a neutron star is when a star explodes, as I said, in a supernova explosion. Most stars are not like the sun. Most stars do not occur. The sun occurs by itself. We don't have a second star in our system. Most stars in the universe occur in pairs or triples. And so if you imagine you have two stars that are orbiting each other over time, one of them goes supernova, and it keeps orbiting. You have now a neutron star. The other one will eventually go supernova. You have two neutron stars orbiting each other. So this is a nice configuration because eventually over time, due to tidal features, they will get closer and closer and closer until they merge in a massive explosion that produces these elements. And this is an example here. This is an artist's conception. You may have seen this all over the news last year. When they merge, the merger is such a big gravitational thing, it produces gravitational waves. And so the gravitational waves from one of these mergers was first found last August 17th, 2017. This was found by the LIGO detector. They actually saw the gravitational waves. And then our astronomers in Chile actually saw the light from the two neutron stars actually merging. And this is it. That tiny little blip, it doesn't look very impressive, but it's 40 million light years away. That little blip there is two neutron stars in the process of merging. But the interesting thing about this is the first time we've been able to actually see elements like gold and platinum, the process that's going on. So you may be asking, well, there's gold and platinum here on Earth, right? I have gold and platinum. That's because the sun has had hundreds of thousands of generations of stars before us. So you, in fact, are the product of not just one or two of these supernova explosions. You're the product of 100,000, probably, generations. And in that time, a few of those were, in fact, neutron star mergers. Now, gold and platinum are, of course, very rare on Earth. But if you were at one of these explosions, that explosion, where you take these two neutron stars and put them together, produces about 200 Earth masses of gold. So let me put that together. One explosion produces 200, take the Earth, turn it all to gold, 200 times 200 from one of these explosions. So if you really want to find a lot of gold, you'd want to go near one of these explosions. It's so rare on Earth because, unfortunately, over time, it's been very diluted. Anyhow, this is very exciting work. This is the first time we were able to see this ever. Okay, let me end by saying one of the things I think you hopefully got from the beginning of the talk, the amazing work of Edwin Hubble and other astronomers was due to the fact that we had great telescopes at Carnegie. And we are continuing that tradition by building the next generation telescope called the giant Magellan Telescope. And you may have heard about it from some of the astronomers here, but I want to take a minute or two to talk about it. This is the equivalent of an 80-foot telescope, which is pretty big. I'll tell you, so our telescopes in Chile now, the biggest telescopes we have are the equivalent of one mirror on this telescope. This mirror has 7 such mirrors, so it's a huge leap over our biggest telescopes now. And the reason that you have 7 mirrors as opposed to one mirror is you just can't make an 80-foot mirror anymore. There's just no way of having that work in any realistic way. So the 7 mirrors all work together to effectively form a single surface. This, to give you some ideas here, the dome on this telescope is about 24 stories high. It's a pretty big telescope. Okay. Anyhow, this is being built and will be on our site in Chile. And we're actually making some pretty good progress on it. But let me just briefly remind you, I could have even put this at the beginning of my talk. Well, why do you build a big telescope? By the end of the talk, I think you'll probably know, right? The first thing a telescope does is it collects light. And so the bigger the telescope is, the more light, the bigger the mirror is, the more light you collect. If you were going to collect rain, putting out a bigger bucket collects more rain. You should think of a telescope the same way, it just collects light. In the case of this telescope, it will collect light about 100 times faster than the Hubble Space Telescope. So to give you an idea of what that means, this means this telescope is sensitive enough that it could see a candle at the moon. That's pretty impressive. Yeah, yeah, it's kind of crazy when you think about that, yes. A candle at the distance of the moon. Yeah, anyhow. But collecting light, so why is collecting light important? Collecting light is important because if we want to see those very, very faint galaxies, this is the way you do it. You need to see the very first galaxies in the universe. We need a telescope like this. The other science case, which I'm not talking about at all today, but the experts are here in this building, are studying nearby planets and studying the atmospheres of those planets around nearby stars. An amazing, probably the reason to build this telescope. And that, like I said, is being worked on here. This telescope will allow that. The big collecting area allows that. But the other thing a telescope does is it allows you to resolve things, that is, see detail on small scales. And this is very important. So right now, the Hubble Space Telescope is the standard for that. This telescope is about 10 times better than that. My analogy here is one I usually give in Los Angeles, so I'll do it from Los Angeles. But with this telescope, you could observe, if you had the telescope in Los Angeles, you could resolve a dime at the distance of Las Vegas, which is about 200 miles. So what's the example equivalent here? Here in Philly, and Philly's probably not even, yeah. Imagine pointing a dime in Philly and trying to be able to resolve it and tell the difference between a dime and a nickel, for instance, the surface. This telescope will allow you to do that. It's truly an incredible telescope. It will be. Okay, just to show you quickly, here's some progress on the mirrors. The mirrors are made by our partner, the University of Arizona. Mirror 1 is done. Here's mirror 2, 3, and 4, 4 and 5. Mirror 4 is the middle mirror. You can see the hole in the middle there. And then I have a really great animation here. This is not animation. This is a video. This is how we make the mirrors. You have a big casting unit with thousands of pieces of glass. You heat it up and spin it. And you basically, this is how you form the structure that ends up being the mirror. That view was good. Here's the great view. This is within. You can actually see the pieces of glass melting. I've seen this video maybe 200 times, and I always love it. It's just such an incredible that they could do the video. And so here again, it'll go through again. I'll let you see it again. So it is somebody's job to go through the thousands of pieces of glass and actually make sure the glass has the right properties. I don't know who does that, but that's not the most exciting job. But I should point out, once you make the mirror, or you make the glass, it cools for about 8 to 10 months. You then still have to shape it. You still have to do some grinding to get the right shape for the telescope. And then, well, how does it become a mirror? This is see-through. It becomes a mirror by putting a thin layer of either silver or aluminum on the surface. Then it reflects. Anyhow, it's just truly spectacular work. And as I said, we're making great progress on the mirrors. Oh, here's another little animation. This is an animation. This is on our mountain in Chile. And this has actually changed a little bit. But the reason I like to show this animation is to remind people, this telescope will be over $1 billion. It sounds very expensive. But remember, it's a 24-story structure that rotates and points, right? Both the outside and the inside. This is an engineering marvel, really. We spent a lot of the money is actually in engineering. And remember, it's also one of a kind. You don't just go and order this off Amazon, right? I mean, you just can't find these parts. The mirrors alone take about 3 years to do the whole process for a mirror, and it's about $20 million. And so it adds up over time. The other thing I like to show about the dome is you see the dome is open. If you go to a modern telescope, you'll see the domes are open. And this is because we've learned that the old closed domes are terrible because the old closed domes hold in heat. And if you have a temperature difference between the outside and the inside of your dome, it blurs your images. So we have airflow through the telescopes now. Anyhow, this telescope is hopefully having first light in about 2023 or 2024. We'll be very excited about that. Okay, so this is my final slide, I think, or close to it. For 114 years, I think I got that math right, yes. Astronomers at Carnegie, both here at DTM and in Pasadena and in Chile, have really led our efforts to understand the universe. I go through this. We basically discovered the universe. That was Hubble's results. We discovered it was expanding. We discovered it was accelerating. We discovered it was filled with interesting material, exotic material like dark matter and dark energy. That's a pretty huge list right there, right? And this is not even talking about some of the work on, for instance, planets around other stars that Paul and others are doing. This is what happens when you have the freedom and you hire the best people that we have at Carnegie and you give them the amazing telescope facilities. Telescopes are really important for this. And with the giant Magellan Telescope, we will continue to remain on the forefront for many, many decades to come. And I just point out that if you're interested in Carnegie astronomy, all of our stuff, we are on the standard Facebook, Twitter, Instagram. You can follow Carnegie Astronomy. We have other ones. I don't know what the other ones are. Carnegie Geo, probably you guys know them all. Planets, there's a whole bunch of them. Go to our main website, the Carnegie Science website, and you can find all those. And I encourage you to follow those and hear more. And I will stop there. Thank you. Any questions? If there are no questions, that would be bad. Okay. I'm afraid to see what Yushen has to say. Okay.
No, I have a
Go ahead.
simple question.
Yes.
The glass melt, you have these shapes.
Oh, yes. Yes. The hex. Yes. The structure ends up being very good for the support of the instrument. In terms of supporting the mirror, I'm trying to find an image. Where's that image where they have them? Was it in the video? I guess you have to see the video to do it. But well, let me point that out one thing. So that structure is, these are really light mirrors. This is the other amazing thing. The way this technique works, they're actually not very heavy. The old mirrors were made of like solid glass. But that structure ends up being very easy to also move in a sense, because what we do with these telescopes, all modern telescopes, you can see it in this image, that's why I put this up here. On the back end, you see these things here. These are actuators. We actually, the telescope in real time, we are continually putting pressure on each of those little units and deforming the shape of the mirror. This is an exaggeration, of course. It's very, very small. But that's the way we can actually do some corrections in real time for temperature changes. We use this technique even on our Magellan telescopes, and it's very effective to get good image quality. That's not such an easy question, by the way. Yeah.
When you talk about neutron stars coming together,
Yeah.
producing the more dense elements.
Oh, sorry. I'm supposed to. Yes.
When you talk about neutron stars coming together, excuse me, and producing the denser elements, neutron stars themselves are neutrons. They
Yes.
are not elements. They don't have elements
Right.
in them.
Right.
So when two neutron stars come together,
What are they doing? Yeah.
What's producing the higher elements, and why are they being thrown out? Presumably they're being thrown out into space. So how does that mechanism work as well?
Yeah, you are I'm way out of my field of expertise on this. One of the world's expert on this is in my building, and I have to have him. Actually, he is coming to give a talk at Peachtree, our headquarters in September, which I would highly recommend you come to because he can explain it in detail. In fact, elements aren't from the initial explosion, but over time, as this causes an explosion, which is then kind of expanding, it has something to do, as the material cools, my guess is that you start actually breaking down into the individual parts. So you get more than just neutrons. But honestly, the details I don't really know. I don't think anybody fully understands the process. There's, in fact, a lot of people still trying to understand it from a theoretical standpoint, was what I would say. Yeah, I know, it's a terrible answer. I'm sorry.
Getting back, is it on?
Yes.
Getting back to the mirror, when that glass is melting, the chunks of glass, I know from working with stuff like that you get air trapped in it. So I noticed there wasn't any air trapped in there, and I'm thinking, was that done in a vacuum?
It's done in a chamber, so there's a specially designed. So the video here, you see, it is done in a chamber that probably is vacuumed. Yeah, yeah. You guys are getting way outside my expertise. Sorry, let's go over here. I guess. Do you want to? Sorry, what's easiest? Sorry, hold on a second.
What are the advantages and disadvantages of the different kinds of telescopes,
Yes.
like Hubble and Webb?
Awesome. I should start putting that in my talk, because somebody always asks me the question. The question was, what are the advantages of different types of telescopes? Let me answer a specific question, which is the advantages of space telescopes versus ground telescopes, because I think that's the more general question. The Hubble Space Telescope is like our telescopes in Chile and like the Giant Magellan Telescope. These all use visible light primarily. So the difference is, by being above the Earth's atmosphere, you don't have to worry about the atmosphere. The atmosphere tends to blur images. So the reason Hubble produces such spectacular images is because it doesn't have that blurring from the atmosphere. However, the next generation telescopes actually will have the ability, we believe, using adaptive optics to correct for that. So we think we can correct for the atmosphere in real time. And so we think that's how the image quality can actually end up being better than Hubble. But let me say the real difference between a space telescope, like if you could, you would put everything in space. because why bother with the atmosphere? Why correct for the atmosphere if you can get above it? The problem is price and size. So the Hubble Space Telescope is the same size as a 100-inch telescope, 100-inch, 2.5 meters. It is the same size as the telescope that was launched. Hubble was launched in 1990. Is the same telescope that Edwin Hubble was using back in 1917 at Mount Wilson. So it took, you can see just the difference in size. Oh, it took 80 years to be able to launch a space telescope the same size as what we could build on the ground. It's easy to build bigger ground telescopes, but the price difference is what really matters. The next generation Hubble, which is called the James Webb Space Telescope, which you probably hear a lot about here, is being launched now in 2020. That telescope is the same size as our current telescopes in Chile, or basically effectively one mirror from the GMT. That telescope is already $10 billion. We built our 2 telescopes in Chile, 2 6.5-meter telescopes, for $32 million. So $32 million versus $10 billion, just to show you the price difference. So I think the thing is it's hard to do it in space because size-wise, but it's so much more expensive. It is an infrared telescope. I'm just using it from a size standpoint. Yeah, yeah. There's a reason to go to space for that. Yeah.
I think one of the greatest things that could happen would be to find some sign of life somewhere in the universe.
Yeah.
How optimistic are you that would happen in my lifetime? Because I won't be here forever.
Yes. So the thing is I have to be careful because there's probably better experts on this campus than me. But I tend to be an optimist on this issue. And in fact, this is one of the primary drivers for building a telescope like the Giant Magellan Telescope. What I will say is, well, let me 2 arguments here. One, is there life in the universe besides us? I will remind you of the picture of the 3,000 galaxies in that pinch of the sky, each with 1 trillion planets, and say, if there was not life in the universe elsewhere, it would be truly remarkable. The sheer statistics seem to me that it's quite likely. I also believe that, based on what we see, life may have happened, or I think folks here probably don't believe so much on Mars, but we got close to having life on Mars if we didn't. So that's almost 2 planets in 1 solar system that had life. So if you think about all those solar systems, my opinion is that life is probably pretty prevalent. Now that said, how do you detect it? And so the answer is you can detect it with the next generation telescope like this by looking at the atmospheres of exoplanets, planets around other stars that people here are working on, and actually looking for the signatures. There are biosignatures that one expects. I think there's still a big debate about those signatures. We still have to understand that. There's a lot of work to understand what do we expect to see. What would be a unique signature of life, for instance, versus something that could happen naturally. But I do think we'll find that, and I do think that in the next few decades it's entirely possible with these telescopes we'll see it. I'm an optimist. Others do not agree. But I would say that there's a good chance in your life you'll see evidence. And then that's opens a whole other realm of things, of course. Let's see, where do we have, we'll go back and forth.
I was wondering why it is that with this discovery of black holes at 13 billion years of age,
yes,
why that doesn't lead you to question the calculation that the universe is only 13 billion years in
13.7 billion, yeah. Well, because the 13.7 comes from several different arguments. There are several different methods that have been used to estimate that, completely independent, and they all get to come to the same answer. I think what it tells us is that we don't understand is how do galaxies themselves form. And so my guess is the fact that every big galaxy like the Milky Way has a big black hole in the center tells you that there's some relation between the formation of a galaxy and the formation of the black hole. The best models suggest that early on in the universe, the very, very first stars were very massive, so massive that they collapsed the black holes over very short time periods, I mean millions of years or shorter, and that those then were the seeds for the black hole. But I have to say that this object is a challenge to the current models. So I think the next generation telescopes will allow us to see the very first galaxies and really be able to test, But the evidence for the 13.7 is really quite strong. Let's see. Anybody back there you want to give the mic to? There's a whole bunch.
Let me pass this over to this young man and let him ask a question, and I want to follow on to his question.
Uh-oh, a two-parter. That's not good.
So with back to the telescope in Chile,
yes.
How much data would be collected every day or so, and what exactly would they be looking for with the telescope?
Oh, that's an interesting question. Are you looking for size? It's an interesting question. So when you build a bigger telescope, you can do lots of different things with it. One thing, a bigger telescope allows you to study an object faster. So for instance, when I say that this telescope collects light 100 times faster than the Hubble Space Telescope, what that means is that something you could do with the Hubble Space Telescope in a few hours would take day or 3 weeks with the Hubble Space Telescope. You'd be able to do it in a couple hours with the GMT. So one thing is you can just do things faster. That's not really interesting. I think the thing is you really want to do things that are much harder, things that are very, very faint. So in fact, I think the telescope will spend a lot of time pointing at the same object. So in terms of collecting data, it may not actually collect a lot more in terms of for instance, objects observed, because you're going to take longer to observe those objects. I can give you another example. In the case of Edwin Hubble's expanding universe work, what he did, the measurements he took, some of the data he took, he would spend 3 or 4 days observing a single galaxy with that telescope, because that's what it required. And now we could do that in like 5 minutes. So, I think, but going long may be what we end up doing to kind of see the harder things. I don't know, that's a little bit vague, but hopefully good enough. And now I have the follow-up. Let's see what the follow-up
Well,
is.
this is not about that.
Okay.
Okay,
good.
You got all these scientists in the room. I'm an economist, so
Yes.
looking at this, you talk about 10 billion here and
Yeah.
100 million over there and
Brilliant,
all that.
yes.
So this is, you're adding up to real money. So how do you calculate all the investment in this, and then getting to practicality? How does that here on Earth have a real impact in the economies, not only here but Chile and many other countries across the globe? Because we're investing in something. So
sure. Well, what I would say,
not just knowledge, but I mean real economies.
What I would say is, we're getting lots of galaxies for a very small price. I mean, the price per galaxy is pretty good, actually. It's one way to look at it, right? It's cheap. It is. It is. It's a really good question. I've had a few people ask me, you didn't ask it in a rude way, your way was fine, but I've had people ask me, I had somebody once say to me, why would we do that? Why are we spending money on that? And I said to her, it was at an art party, so I said, well, astronomy in some ways it's a human enhancement activity similar to art and music. And she said, that makes sense. I mean, I think being able to understand our place in the universe is an interesting and very important thing. Now, the world is not filled with astronomers. It's not like, one out of 5 of us in the world is doing astronomy. This is still a very small field. So I think that's an investment worth making. In terms of technologies, though, a lot of technology that you use has come from, of course, the space program. I don't want to say this, but the Hubble Space Telescope is an amazing instrument for astronomy. There are Hubble Space Telescopes looking down at us all the time that the military uses. There are many applications that come from the technology to develop the telescopes. That would probably be the closest in terms of actual real. But astronomy is a tiny blip on what we spend money on. And I think it's worth it just to kind of understand where we are and who we are. And at some point, you may rely on us because we may need to move. And if we need to move, you want to know where to move to. That won't happen in my lifetime, I don't think.
When I was in the 5th grade, I wrote a report on the construction of the Hale telescope.
The Hale telescope, okay, that's the 200-inch, yes.
200-inch one
Yes,
in Palomar.
yes.
So I am interested in how they're building the mirror for this. How big are each of those segments?
Yes.
How are they going to move it to Chile?
Oh, great, two great questions.
How are they going to shape the parabola so it'll collect the light or whatever it is you're going to
Yes.
collect?
Yes.
Are they using all those little lumps that I'm seeing in that segment 2 to shape it a little? Because the mirror is so thin, or how are they doing all of this?
Yeah, well, all the above. There's a lot of questions there. The mirrors are about 25 feet across, which turns out to be about the biggest size mirror you can make and actually still control it in a way and keep the shape in a way. And that's why the size works out. And the 7, of course, is a configuration that's easy because you have the circle and then the one in the middle. So they're about 25 feet across, which is pretty big. Those are like the biggest mirrors we have now. That was one question. In terms of the shape, the overall shape, the outer mirrors actually have a very funny shape. Normally a telescope is kind of like this, it's kind of symmetric. This case, the 7 mirrors combined have to do that same shape. So the outer mirrors actually have this very weird edge. And so in fact, no one had ever made such a mirror like that before. So we made the first mirror, segment 1, which you'll see is done, was made early on in this project to make sure we could actually do it. And we had. It turns out that you can test it and it's fine. So you can't, for instance, switch the outer mirrors with the inner mirrors because there is the shape, but the shape comes from combining them together. By themselves, the mirrors aren't terribly interesting. You really need all of them to make it work. How do you move it? Yes. Yeah. Oh, that was the other. I'm trying to remember the questions. Yeah, somebody always asks me that question too. Very carefully. You put them on a truck in Tucson and take them from Tucson to Long Beach, which for those of you who don't know California, Long Beach, California, is just south of Los Angeles. And that is already a test because remember they're 25 feet across. And so you have to find a path to get there without an overpass. That is right. And it is still a problem now, but there is apparently a way to get from Tucson to Long Beach. I don't know how to do it, and I wouldn't want to do it. But there is a way to do it. Then you put them on a ship, and then you ship them down to Chile. And then on the other side, there's a port about 3 hours from our observatory where you get them out, and then you ship them up the mountain again, driving them. But this is and there's a question, do you do 4 at once? Do you do them one at a time? You know, part of me goes, well, I wouldn't want to have all 7 on a ship and have that ship something, you know what I mean? You spent 10 years building these things. I don't really know that process. My guess is we'll probably do the first 4 and start testing the telescope with 4. You can do some stuff and then do the other 3. But I'll be retired, I think. Well, maybe not actually. It's not that far away. Was there another question here?
Am I on? You emphasized the emptiness of space,
yes.
And also that the solar system is going to be around for a long, long time.
Hopefully.
What is the possibility of the solar system being influenced by events outside of it, like a nearby supernova,
yeah.
a wandering star, radiation bursts, that sort of thing?
Yeah. So there are people who work on this quite extensively. There are people who believe that the mass extinctions on Earth are kind of in a very regular pattern, and that it has something to do with stars coming by or something and sending comets towards us. I mean, that really is, I don't know what that work is. It's not, yeah.
Not accepted.
Not accepted. There you go. I'll apologize. I think there's, of course, always a danger. The bigger danger for us on Earth is actually an impact within our solar system. We know, you'll remember the comet that, Hale-Bopp, was it? Hale-Bopp? The one that hit Jupiter in the 90s, you remember? We saw in real time. If that happens on Earth, that would be an issue. So that's, I think, a bigger issue. You should be more worried about that than Andromeda and the Milky Way merging. That's what I would say. So there is some danger there. I think we don't really know. I mean, there's some people, I think as Rick said, I would say most of those theories are kind of on the fringe. Is that the nice way of putting it? Yes, that's the polite way of putting it. But it doesn't mean they're wrong. It just means that they're not widely accepted. That's the one I was thinking of. Thank you. Hale-Bopp is another one. Yes.
Hale-Bopp was one that went by, it showed up in the sky.
That makes sense, yeah. I knew it didn't sound right when I said it. This is when you know you're getting old. You can't remember from 1990 something.
Yeah, hi. I'm neither a scientist nor an economist, so.
Excellent. You're not a lawyer, are you?
And I'm not a lawyer.
We have a lawyer here, so at least one. Actually, 2 that I know of.
I do chair something called the Arthur C. Clarke Foundation, and we've come a long way since then. But you alluded to a potential role that dark matter
yes.
plays, particularly around that plays in the universe, but it's 96% of the universe.
Of the stuff in the universe,
right.
Yeah.
What are the prevailing theories of what dark matter might be, or how we might discover more?
Right, and so let me also clarify that 96% is the dark energy and the dark matter. Mm-hmm. So the dark energy, I'd say we know, the dark energy is this force that is accelerating the universe. And I would say we actually know very little about that. I'm not confident with any of the theories, but that's been around not very long. Barry Rubin's work dates from the early 70s, and so we've had kind of almost 50 years to be studying dark matter, and I think we have a good idea. But we have a good idea of what it's not. And so in the case of dark matter, we can eliminate things like rogue planets, just the space filled with planets, or black holes. There are observations the astronomers can make that can kind of eliminate almost anything astronomical. So at this point, we believe it's some sort of particle that we don't yet know about, some small particle that is in large numbers, and so that the mass adds up. The key is it doesn't interact with regular matter like us. So dark matter is presumably flying through here all the time, but we don't detect it because it doesn't interact with what we're made of. And so I think that the answer to the dark matter question is really a physics problem. Vera first identified it. Many of us have spent our careers, I spent a lot of time on dark matter. We've kind of characterized it in astronomy. We can now hand it to the physicists and say, what is it? Because it's going to come from some experiment, I think. I don't think for astronomy we're really going to learn much more, except that we know it's there. I hope that was okay, yeah. Sure, do you want to, I don't know.
Let's just take one more.
One more question. Oh, sorry, I think it's the one behind you. Yeah.
How do you schedule it?
Great question.
What do you do with the data? How long is it proprietary? How do you share it?
The telescopes, yeah. This is a really relevant question. I'm surprised somebody didn't ask me this question. Chile's very far away, and I think I mentioned it takes 24 hours to get down there. So the first question people usually ask me is, well, why do you have to go to Chile? And the answer is, in theory, you don't. In fact, some of the astronomers here at DTM actually use the telescopes remotely. We can do that, but for me, a night of telescope time is worth almost $50,000 if you add the price of the telescopes and everything. It's pretty substantial. So for me, it's really worth going down there. If I get 4 or 5 nights, it's a substantial amount of money to invest. And I think there's nothing like being at the telescope to actually understand the data. And the other thing is sometimes you change your program depending on the weather. And plus, you get to look at those beautiful stars. I mean, there's a lot of reasons. And you're not distracted by everyday life. So for me, as an astronomer, I'm from a generation that really loves going to the telescope. Younger astronomers don't feel this way. Most of them, they've grown up in a world that's very connected, and they're just kind of like, why do we have to bother? So I think the future is telescope, most observing will eventually be remote. So astronomers will not go to Chile. In terms of the scheduling, the way we do the scheduling at Carnegie owns, this is a very rare thing to be a Carnegie astronomer. We get very significant amounts of telescope time, more than anybody else in the world. If you come to Carnegie, you're going to do really well because that's the whole point of coming. We have these amazing facilities. And so typically, everybody gets some time, but there's a competition. Everybody writes a proposal. We decide who is best. And then it is scheduled based on kind of scientific ranking. But people are usually assigned nights in the case of that. Our data, because Carnegie is an entirely private organization, we don't necessarily release data to the public after some period. That's something we're actually looking at because we really would like to do that. But to do an archive is actually very expensive. And so I haven't been able to come to the point where, you know, if I, for instance, I've been talking to people about partnering with somebody who could do the archive because that's kind of out of our mission. That would be something we would think of doing. One more question, I know. Oh, he's going to have a hard one of these. Yeah. I was on the tour with him. He knows a lot of stuff.
Since you're confident that there's life randomly produced in the universe and we'll discover it sometime, maybe in our lifetime, why is it or how close are we coming to producing life ourselves with our own hands in science here on Earth?
Yushen, do you want to comment on that one? We have a biologist here who probably can answer it. I seriously make you do it. You have a mic right there. Because I don't feel qualified to answer that.
There is a fairly, I would say still fairly small field trying to create self-replicating entities. You can call it cell. But it's really, I would say that's what the group of people trying to understand origins of life. And there some theories about life started with RNA. And then if you can enclose RNA and have some chemicals in there, maybe they're going to self-replicate. So, yeah, that's happening, but it's not a big field. Yes.
There are people trying to do it. One of the wonderful things about being a Carnegie scientist, particularly this evening, is go ahead.
Actually here in our geology department, there are 2 scientists that are really studying the origins of life. Yeah, I'm from embryology department. What we do is life is already becoming very complicated, but it's definitely interesting for us to also try to think about how we can work with our geologists to look at that problem.
Yeah, she was saying pretty much what I was going to say is having the broad range of science that we do at Carnegie is very valuable. So we have biology, geophysics, and geology, and then planetary science. We kind of do everything. And so it's very valuable because between us, one of the interesting things I think at Carnegie is trying to bring together these various areas. And questions like life, actually, the origin of life, really impact all these areas in some way. So it's some very exciting stuff in the future.
I think you just previewed a future neighborhood lecture.
Yes, that would be really interesting, actually, yes.
So the next neighborhood lecture is, I've forgotten the date, it's in towards the end of May. It's Tim Stroll from the Geophysical Laboratory, who does amazing work actually thinking about ways to make new materials. So you think about steel and things that we've known forever. This is not what Tim does. Tim looks at the way you can rearrange atoms and make materials with new properties. So I would encourage you to come to that one. And at that point, let's thank John again.
Thank you, everybody. Excellent. That was fun. Very different questions than I usually get, so it's kind of fun. Yeah, sorry.